Hello everyone, welcome back to the MP Coding Linux Device Driver Development with Raspberry Pi tutorial series. In this video, we will discuss wait queues and how they are used to implement blocking and non-blocking I/O inside a Linux device driver. Before understanding wait queues, we must clearly understand what blocking and non-blocking I/O mean in the context of a Linux driver. What is blocking I/O? Blocking I/O means that when a process calls read and the requested data is not available, the process is put to sleep until the data becomes available. This is the default behavior in Linux. The kernel suspends the process and frees the CPU so other tasks can run. The process remains in a sleep state until the driver explicitly wakes it up. A common example is a read call from user space. If the driver does not have data ready, the process sleeps inside the driver and the read call does not return until data becomes available. So what is non-blocking I/O? Non-blocking I/O means that the system call returns immediately, regardless of whether data is available. If data is available, the driver returns the data. If data is not available, the driver returns -E again, the error indicating resource temporarily unavailable. In this case, the application is responsible for deciding what to do next. Typically, the application will retry or use mechanisms such as select, poll, or ePoll to wait for the device to become ready. To enable non-blocking mode, we use the O_non-block flag. When a process opens a device in non-blocking mode, or enables it later using the file control interface, any read or write operation that would normally block must instead return immediately with the error -E again. In other words, the system call will never put the process to sleep. There are two common ways for a user space application to enable non-blocking mode. Method 1. Set the flag on an already open file descriptor. Method 2. Set the flag at open time. Once this flag is set, if the application calls read, the call will never sleep. If data is available, the driver returns the data. If data is not available, the driver immediately returns -E again. Now, let's see how this behavior works using a simple example. First, I created the makefile and the kernel module source file. Now, if we look at the source code, currently this driver contains the basic character device driver implementation. First, the driver allocates a character device region. Then it initializes the file operation structure and attaches it to the character device. After that, the character device is added to the kernel device list. Once the device is registered, the driver automatically creates the device node inside the /dev directory. I already explained all of these steps in detail in my character device driver video in this series. If you do not clearly understand these steps, I recommend watching that video first. Next, this function called external GPIO IRQ setup configures GPIO 20 as an input pin and also sets up a GPIO interrupt. I have connected a push button to this GPIO 20 pin. If you are not familiar with how to configure GPIO interrupts or connect the hardware, please watch my GPIO interrupts video in this series, where I explain that part step by step. At the moment, the GPIO interrupt service routine simply prints a message to the kernel log whenever the button is pressed. So right now, the interrupt handler is working, but it only logs a message. Now let's move to today's implementation. Currently, only the open and release file operations are implemented, and those functions simply print messages to the kernel log when the device is opened or closed. Now, the next step is to implement the read file operation, which will demonstrate both blocking and non-blocking behavior. First, go to the file_operations structure definition. There we can find the read operation prototype. Copy that definition and paste it into our source file. Next, change it to static and name the function my_read. This function takes 4 parameters: a file pointer, a user space buffer, the requested read size, and the offset pointer. Inside the function, the first thing I will do is print a message to the kernel log indicating that the read call occurred. Next, at the top of the file, I will declare a static integer variable called data_available and initialize it to 0. Here, 0 means no data is available. Then inside the GPIO interrupt service routine, I will set this variable to 1. That means when the button is pressed, data_available becomes 1, indicating that new data is ready. So now, whenever the button interrupt occurs, the driver knows that data is available. Now let's go back to the my_read function. After printing the message, the first step is to check whether data is available or not. If data_available is 0, it means there is no data yet. In this situation, we must check whether the device was opened in non-blocking mode. We can check this using the file flag stored in f_flags. If the o_non-block flag is set, that means the device is opened in non-blocking mode. So in that case, we print a message indicating non-blocking mode and immediately return -e again. This is the rule for non-blocking I/O. The driver must not sleep and must return immediately if no data is available. Now, if the device is not opened in non-blocking mode, that means we are in blocking mode. In this case, we print a message and put the process into a wait loop. Here I use a while loop that keeps checking data_available. While the value is 0, the loop calls CPU_relax. This creates a busy wait loop, meaning the process continuously waits until data becomes available. However, this is not the correct way to block inside a driver. Later in this video, we will replace this with a proper wait queue mechanism. For now, I am intentionally using this approach so I can show you why this method is wrong and why the wait queue mechanism is necessary. Now let's continue with the logic. When the button interrupt occurs, the ISR sets data_available to 1. So when the read function detects that data is available, it resets data_available back to 0. Next, we need to send some data to user space, using copy_to_user. For that, I will create a static character array containing a simple message, hello from kernel. Now pass this message to the this copy to user. If copy to user fails, the function returns -e fault. If the copy is successful, the function returns the number of bytes copied, which is the size of the message. Finally, we add this function to the file_operation structure by assigning .read equals my_read. So now our read operation is implemented, and it supports both blocking and non-blocking behavior. Now let's build the kernel module. The build is successful, so now we can move to the user space test program. I have created a simple program called test_nonblock.c. Currently, it is just an empty template that includes the required header files, such as stdio, file control, unistd, errno, and string. Inside the main function, we will first open the device file in non-blocking mode. The device file name will be provided as a command line argument from the user. So we take first argument, open the file in read-only mode, and also set the o_non-block flag. If the open call fails, we print an error message and return the error. Next, we create a character buffer to store the message coming from the kernel. Here I declare a buffer array with a size of 64 bytes. After that, we call the read function to read data from the device and copy it into the buffer. Then we check the return value of the read call. If the read fails, we print the error message using string error and pass the error number, so we can see exactly what went wrong. If the read succeeds, we print the contents of the buffer, which should contain the message sent from the kernel driver. Finally, we close the file descriptor and return from the program. The functions open, read, write, and close are standard file operations in Linux user space. I have already explained these in detail in my file operations video in this series. If you are not familiar with these functions, I recommend watching that video as well. Now let's build the test program. I compile it using GCC test_nonblocking.c-o test. The build is successful and the test executable is generated. Now let's move to the testing part. In another terminal, I will monitor the kernel log so we can see what happens inside the driver. First, I load the module sudo insmod blocking_non-blocking.ko. The module loads successfully. Using udev, the driver automatically created a character device node in the /dev directory called my_cdev0. Initially, remember that data_available is set to 0, which means no data is available yet. Now let's run the test program and pass the device file path as an argument. Sudo space dot /test space /dev /my_cdev0. In the console output, you can see the message, read failed, resource temporarily unavailable. If we look at the kernel log, we can see that the device file was opened, the read call was executed in non-blocking mode, and then the file was closed. This is exactly what we expect. Because the device was opened with the o_non-block flag and data_available is 0, the driver immediately returns -error again without putting the process to sleep. Now I press the button connected to the GPIO. In the kernel log, we can see that the GPIO interrupt service routine printed the message GPIO interrupt occurred. That means data_available is now set to 1. Now if I run the test program again. This time the console shows read success. Hello from kernel. The kernel log also confirms that the read operation was executed successfully. This happens because data_available is now equal to 1. So the driver skips the blocking check, resets data_available back to 0, copies the message to user space, and returns the data. So this demonstrates how non-blocking mode works. If data is available, the driver returns the data immediately. If data is not available, the driver immediately returns -error again, without putting the process to sleep. Now let's see what happens when we open the device in blocking mode. For this test, I will simply use the cat command. So I run sudo cat /dev /my_cdev0. The cat process opens the device without the non-block flag and continuously calls read in a loop. Now let's look at what happens inside the driver. Since data_available is 0, the my_read function enters the blocking path and starts spinning in the CPU_elapse loop. Now I press the button. The GPIO interrupt service routine runs and sets data_available to 1. At that moment, the busy wait loop exits. The driver resets data_available back to 0, copies the message to user space, and the cat command prints hello from kernel on the console. Immediately after printing the message, cat calls read again, which sends the driver back into the busy wait loop. So every time I press the button, the console prints the message hello from kernel. This demonstrates the blocking mode. However, there is a major problem with this implementation. Right now, the blocking behavior is implemented using CPU_elapse, which creates a busy wait loop. If I now try to interrupt the cat process, it does not respond. For example, if I press Ctrl+C, nothing happens. If I open the new terminal and run top, we can see the cat process running and consuming 100% CPU. And its state is R, which means running. The process is continuously spinning inside the kernel. Now suppose I try to remove the module using sudo rm mod-f for force to stop and driver blocking_non-blocking. Even that will not work. The reason is that the cat process still holds an open file descriptor to the device, so the module reference count is not 0. The kernel refuses to unload it. Even a forced removal will fail because the process is still spinning inside the driver. The root cause is that the busy wait loop never returns control to the kernel scheduler. Because of that, signals, module unloading, and process cleanup are all delayed indefinitely. So how can we terminate the process? One option is to reboot the system. But there is another way. First, we identify the process ID from the running processes. In my case, PID for cat process is 4541. Then we can check its state using ps-lp space PID. In the state column, we can see the process state. Here it shows R, which means the process is actively running on the CPU. Now I try to kill the process using sudo kill-9 space PID. But nothing happens. Even kernel log nothing indicates. Now watch what happens if I press the button again. As soon as the interrupt occurs, the driver exits the busy wait loop, returns from the my_read function, and immediately the pending signal is delivered. Now the process terminates, and in the kernel log we can see the device closed message. So why did kill not work immediately? Even signal kill cannot interrupt a process that is spinning inside kernel space. The signal is delivered by the kernel, but the process cannot act on it until it returns from the kernel back to user space. Since the busy wait loop never yields control, the process stays in the running state indefinitely. The only way to unblock it is to trigger the interrupt, which allows the driver to exit the read function. At that moment, the kernel delivers the pending signal and terminates the process. So the key takeaway is this: busy waiting is not acceptable in real kernel drivers. It wastes CPU resources, blocks signal handling, and prevents safe module unloading. The correct approach is to use proper blocking mechanisms such as wait queues. And that is exactly what we will implement next. In the next section, we will replace CPU relax with wait event interruptible and implement a proper wait queue, which provides efficient and signal-safe blocking behavior. Now let's first understand what a wait queue is. A wait queue is a kernel-managed list of sleeping processes. When a process tries to read from a device and the required data is not available, the driver can place that process into a wait queue and put it to sleep. In this state, the process is truly suspended, meaning it does not consume any CPU time. Later, when the data becomes available, for example from an interrupt handler, a timer, or another process, the driver wakes up the processes in the wait queue, and those processes resume execution exactly where they went to sleep. So this is the correct and efficient way to implement blocking behavior in Linux kernel drivers. Now let's see how to declare a wait queue. The wait queue API is defined in the linux/wait.h header file, so we first need to include that header. There are two common ways to declare a wait queue. The first method is static declaration, which is usually preferred for module-level wait queues. In this case, we use a macro called declare wait queue head, and we provide a name for the queue. For example, we can declare something like my_queue, which becomes the wait queue used by the driver. The second method is dynamic declaration, which is used when the wait queue needs to be allocated at runtime. In that case, we first declare a variable of type wait_queue_head_t, and then initialize it using init_wait queue_head. Both approaches create the same type of wait queue. The difference is simply when and how the queue is initialized. Now let's look at how processes go to sleep using wait queues. One commonly used function is wait_event_interruptible. This function puts the current process to sleep until a specified condition becomes true. The important detail is that this sleep is interruptible, meaning the process can also wake up if it receives a signal. There are several variants of the wait queue functions, each designed for slightly different use cases. For example, wait_event sleeps until a condition becomes true, but it is not interruptible by signals. Wait_event_interruptible allows the process to be interrupted by signals and returns either 0 or -error restart sys. Wait_event_timeout adds a timeout, so the process wakes up if the condition becomes true or if the timeout expires. Wait_event_interruptible_timeout combines both interruptible sleep and timeout support. Now let's talk about waking up processes. Once the condition becomes true, for example when data arrives, the driver must wake up the processes waiting in the queue. This is done using functions like wake_up or wake_up_interruptible. The wake_up function wakes all processes waiting in the queue, regardless of whether they are in interruptible or uninterruptible sleep. The wake underscore up underscore interruptible function only wakes processes that are sleeping in the task underscore interruptible state. So the general idea is simple. If data is not available, the process goes to sleep in the wait queue. When data arrives, the driver wakes the queue, and the processes continue running. Now that we understand the basic concept of wait queues, let's go back to our previous example of blocking and non-blocking I/O, and replace the CPU underscore lax busy wait loop with a proper wait queue implementation. Now we will update the same driver to use a wait queue. This is the same source code we used in the previous example. For clarity, I created a new folder and copied the files from the previous example. I also copied the test program and renamed the driver source file to wait underscore queue. This is only to separate the examples for demonstration. You do not need to create a new folder. You can simply modify the previous code. Now let's go to the source file. First, we include the linux/wait.h header file because the wait queue API is defined there. Next, near the top of the file, I declare a wait queue using a static declaration. This creates the wait queue structure that will hold the sleeping processes. I will name this queue my underscore queue. Now let's move to the read operation. Previously, in the blocking path, we used a busy wait loop that repeatedly checked data underscore available and called CPU underscore lax. We will now remove that busy wait loop because it wastes CPU time. Instead, we replace it with wait underscore event underscore interruptible. This function takes two parameters. The first parameter is the wait queue, which in our case is my underscore queue. The second parameter is the condition that must become true before the process wakes up. In our driver, the condition is data underscore available not equal to 0. So if data underscore available is 0, the process will sleep inside the wait queue. Once data underscore available becomes non-zero, the function will wake up and continue execution. Also, since we are using the interruptible version, the sleep can be interrupted by signals. If the sleep is interrupted, the function returns a non-zero value. In that case, we simply return -error restart sys to user space. Now let's go to the GPIO interrupt service routine. Previously, the ISR only set data underscore available to 1. Now we add one more step. After updating data underscore available, we must wake up the processes waiting in the queue. For that, we call wake underscore up underscore interruptible and pass the address of our wait queue, which is my underscore queue. This wakes up all processes that are currently sleeping in the interruptible state on that wait queue. So these are the only changes we need. Declare a wait queue, replace the busy wait loop with wait underscore event underscore interruptible, and wake the queue inside the interrupt handler. With these changes, the blocking process will now sleep efficiently without consuming CPU. Now let's build the module. As you can see, the build is successful. Remove previous load blocking underscore non-blocking module. Then load the this wait underscore queue module. The module loads successfully, and the device node is created in the /dev directory. First, let's test the non-blocking case. The test program has not changed, so we can run it exactly the same way as before. When I run the test application, the behavior is exactly the same as the previous non-blocking example. This is expected because in non-blocking mode, the driver never enters the sleep section. If no data is available, it simply returns -error again immediately. So the non-blocking behavior remains unchanged. Now let's test the blocking case, which is the important part for this example. For that, I will again use the cat command because it opens the device in blocking mode by default. The process enters the read function and waits for data. Now, when I press the button, the interrupt occurs. The driver sets data underscore available to 1, wakes up the wait queue, and the message, hello from kernel, is copied to user space and printed by the cat command. After that, cat calls read again, and the process goes back to sleep until the next interrupt occurs. So functionally, it behaves the same as before, but the internal behavior is now completely different. Let's verify that. If I run top and look for the cat process, we cannot see it consuming CPU time. That's because the process is sleeping inside the wait queue, and its CPU usage is 0%. This is the correct and efficient behavior. Now let's try to interrupt the process. If I press Ctrl+C, the process immediately exits. Since we used wait_event_interruptible, the sleep can be interrupted by signals. The driver propagates this event to user space, and the process terminates cleanly. Because of that, the file descriptor is closed and the module reference count becomes 0. So now the module can also be unloaded normally. This demonstrates why wait queues are the correct solution for implementing blocking behavior in Linux device drivers. Today, we discussed wait queues and how they are used to implement blocking and non-blocking I/O in a Linux device driver. I showed you how wait queues allow a process to sleep efficiently without consuming CPU, and how the driver can wake up the process when data becomes available. This is the correct and recommended way to implement blocking behavior in kernel drivers. If you have any questions about this topic, feel free to ask in the comment section. That's all for today's video. In the next video, we will discuss poll support in Linux kernel modules, which allows user space applications to monitor device readiness using mechanisms like poll and select. So stay tuned, and I will see you in the next video.